Um, so, so we got this individual homework thing going, right? So I wanted to go through that. And then if there's time, I have kind of like course summary slides, you know, that just go through everything we did. But it's actually a ton of stuff. So, so this, so there's two questions. There are two questions with 5 questions in them. So, and they're kind of like standard format. I think this one was in a qualifier, like a PhD qualifier, and this is a new one. So this guy, Hagelson, I think it's, I don't know what his first name is, but he's going to be here Friday. So I was looking up his papers and I found this paper, 2023, Proceeds National Academy of Sciences. That's kind of like Nature, then Science, then PNAS, like the third level citation index, something like 25 or 30 or something, I don't know, maybe 50. So anyways, that's a top level journal paper or whatever. He's given a seminar for chemical engineers at 12:20 on Friday, tomorrow. Like they have a seminar on Friday, the last day of classes. But it should be kind of interesting. It's not on this subject though. It's on microreology. So that's like you take a normal rheology, you take a fluid and put it between 2 plates and shake it, like oscillate at sonic frequency. You can get the stress response. So you have a torque meter. It gets the stress that's either in phase with the oscillations, the sine wave, or it's out of phase. The out of phase would be the viscosity, and the in phase would be the modulus. So it's for viscoelastic materials. Right, so he uses that in here. That's normal. That's normal. A small amplitude oscillatory rheometry. Right, so SAO R, I guess. So that's kind of like the normal way to measure fluids. Then you change the frequency. So the frequency is related to the rate of strain. So you can plot the storage modulus and loss modulus versus rate of strain for frequency. And you get the normal fluid behavior. They would get if you just put it into a cup and bobbin. Right. So the assumption is that this low strain would be the same as kind of a continuous strain. Anyway, so that's in this paper. But the thing he's talking about on tomorrow at 12:20 is microreology, which is you take a fluid with beads in it, and then you look at the Brownian motion of the beads, and you look at it with a laser using some like dynamic light scattering. So you measure the diffusion coefficient of the beads that way, and then basically that diffusion coefficient is going to be related to the viscosity, like the Einstein-Stokes laws, the KT divided, the diffusion coefficient is KT divided by 6 pi viscosity times the particle size. You put in a known particle size, you get the viscosity out of that. You can change the temperature and things. Anyway, from that, there's a way to get the entire spectrum of rheology from that too, not just one measure of viscosity. So basically you put in a loading of particles into it. Anyway, so anyway, that's what the talk is tomorrow. But and he's using that, and then he's doing our AI. Like he's going to take a bunch of data on that. He's going to have like a scanning on that and parameterize from that and like predict something using artificial intelligence, like machine learning, artificial intelligence. So it's kind of like coupling that with this multiple sampling. So might be kind of interesting. It might be kind of a thick, you know. You'll see from this paper that the stuff is a little bit involved. But I don't know. It might be worth seeing. He's from Santa Barbara. So anyway, so this paper though is about this the gel, making gel like Jello, basically. It's a Jello paper. So he has a special Jello where he takes oil droplets, and I think the green is like a surfactant, maybe. I didn't exactly read that part, but he's got oil particles in water. And he puts in this coupling molecule. So it's something like the lamp simulation. Like there's a coupling molecule that you put in, and then that's thermally moving around. So at high temperatures, it doesn't stick. It might stick to one, but not two, or might not stick to any. And at low temperatures, they stick. It sticks to two, and then it makes a network of these particles. Right. Then that'll make a gel eventually. Right. So he's got an experimental setup to do that. I mean, he has this thing, and he did neutron scattering on that, and he determined basically the inner particle potential from the neutron scattering, basically from the separation distance of the beads as a function of temperature. So we got some kind of a potential out of the neutron scattering. And he also got directly, you can get the second Viral coefficient from the low angle, low Q scattering from the thing. So he gets this B2. We can measure it in neutron scattering, and then he does lamp simulations. Now you can tell this is like set up for, it's just almost exactly what that thing you guys did. Like you have a bunch of beads, some sticker molecules. Then it's not polymers, but it's basically skip the polymer part. So if you didn't do the polymer part and just did the beads and the stickers, that's what he did. So it's kind of like a simplified version of the lamps. But he uses lamps. So he kind of should have some idea that how he did that. It's the same thing. So all these things are kind of the same. Like you're always going to start with beads. Then he's going to make them move around and do something. And you're going to look at how whatever the correlation function comes out of this. So from the separation distance of the beads and the lamps, you can model it with it. Or he's putting in, so his input into lamps is a potential, like a 612 potential, or he's using a Morse and two U comma potentials, which are just modified 612s. And you see it's the same thing. It's got a minimum value for the particle separation and the potential. So he gets square well out of the neutron. He gets this thing from the lamp. I mean, that's the input to the lamps. And then from the lamps, from these potentials, then he can calculate. So from the potential function, you can calculate B2, the second Viral coefficient, right? So that's kind of this thing. This explains that a little bit. Another LibreText thing. I'm not sure who makes these things. And this one didn't work. Why? Cannot be found. Oh, that's kind of painful. I have to fix that. Anyway, there is a LibreText thing that goes through exactly how the pair potential. I can just put it basically just gives you that same. This looks like it, right? Yeah, so here's the potential KT minus 1 B2. Right, and this explains what B2 is, like it's a Viral expansion in density. For the ideal gas law, would be the first term. Second term is so B2 has units of volume, right? And then so if you do this for hardcore spheres that don't have interactions, then you just get the volume of the sphere. PV, this rho will be the size of the sphere, which is sigma, is the size of the sphere, and lamps is sigma cubed. So if you have this expression, you want to normalize this by non-interacting sphere, you divide it by sigma cubed. So that expression divided by sigma cubed that's what he uses here. This paper, whatever that is. This is sigma cubed. The rest of it's that expression. Missing the pi's and things. The potential he's putting in is this thing. The things he used for his lamp simulation. So then he can get what he calls B2 star, which is a unitless second Viral coefficient. So what he doesn't say is that it might say in this thing, that by the van der Waals expression, say there. So that's the van der Waals equation. If you equate the van der Waals equation with this series, we did this in class, and then you just solve for B2. So you have two expressions for P over KT, and B2 is the only free parameter. Then you can get expression for B2 in terms of the excluded volume, small b, and the attractive potential between the particles A, right? And that means, so the only B and A are constants, and R is a constant. So the only thing, B2 is just it's another expression for temperature. Like when he plots B2 versus composition, that's a phase diagram, because essentially a plot of temperature versus composition, or quote unquote phase diagram, because it's a gel point, right? So he's going to be looking at B2 star, which is a unitless temperature, because he's removed, because it doesn't have units anymore. If you divide it by the same term, but for like some situation like no interactions. So basically, the no interaction one is just A is 0. There's no potential, and it's just a hardcore sphere thing, right? So that's what he ends up with here, wherever that equation 1 is. Okay. So this is a unitless number. And he's going to make plots of B2 someplace, B2 versus composition, B2 star versus composition. That's like a phase diagram. In fact, in this plot, so then he does also actually a real phase diagram for the system, which is the triangles, and then I think the squares are his B2 thing. And then another thing that he does is the 3 things he does: phase diagram, percolation, and glass. So the glass thing is this blue thing, percolation is the green thing. Percolation means you have the beads moving around, and when they touch, they stick. Diffusion limited aggregation. So they'll just stick, and they'll make like a network, because they're just flying in randomly by Brownian motion, then they hit. So you get a mapping out of the Brownian motion, which is just a random web of pathway of stuff. So anyway, so there's 3 ways you can get a gel, he says at the start. And he cites this guy Cates, who's kind of like the Mick Jagger of science or something now. He's like the latest craze of whatever. So he's supposed to win the Nobel Prize. Everyone will be disappointed if he dies too soon or something, that kind of thing. So he cites Cates here somewhere. So his premise is based on Cates, which is like kind of a good point to start. It's like, I mean, so his premise is like, for example, Cates, blah, 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 blah. So that's his basis of the whole thing, that there's 3 ways you can make a gel. You can do it by phase separation, you can do it by percolation, or you can do it by forming of glass. Which, I mean, maybe they're all the same thing, but basically this is what he wants to kind of demonstrate in this operation. So there's 3 choices, and then everything is going to be in the end like 3 things, like red, green, or blue. So the high concentration is the kind of glassy thing where it locks in. The middle is, I think, phase separation, and low end is the other one, percolation. Right, so he's got like 3: phase separation, percolation, and then phase separation, driving the gel formation. Right, so he needs to. All right, so there's a problem with gelation though, in that it's time dependent. Like it's not at a fixed time. So in other words, if you wait longer, it can take a long time to make a gel, I guess is what it comes down to. Like you set the jello on the table, it's liquid, it's a gel. And if you dilute the jello down, well, you can wait a little bit longer. If you dilute it even more, you can wait a really long time. Right? Or if you make it really concentrated, it makes jello. In fact, it never goes into solution, it's just goo. Right from the start. Right. So basically it's concentration dependent and also time dependent. Right. And then so there's 2 kind of features he's looking at. So he wants to remove the time dependent. So he does that by so he does this B2 measurement either with neutron scattering or with simulation. So he can measure the B2 by this equation from simulation, or he can directly get it from neutron scattering, or he can also use this equation to get it from neutron scattering, because he says he gets this potential, right? And then he gets different gel points for the different systems, by looking at the change in B2. So B2 is temperature. So there's a temperature by the van der Waals equation, there's a temperature corresponding to every B2. So he kind of has like a mapping to go through these different B2s. But it turns out like for one given temperature that he's running the thing, that or one given B2 that he runs the thing, he gets a certain time. Okay, so you can take that concentration, that temperature, and then you can run the storage and the loss modulus versus time. So this is usually plotted against frequency in an oscillatory shear measurement. So 1 over frequency is time. So this is 1 over, so the high frequency would be over here and the low frequency is over there. Or the high frequency is over here, low frequency is over there, which is kind of weird here. Which one is G prime and which one's G double prime? So remember, G prime is closed symbols. So usually at high frequency you get solid, and at low frequency you get liquid. Like if you have Play-Doh and you leave it on the table, low frequency would be you wait a week and it's a puddle, and high frequency would be you throw against the wall and it bounces. It's like solid and liquid, right? So, but anyway, this data doesn't seem to show that. I'm not sure why. It should be solid at low times and liquids at high times, but he's getting the opposite because it's solid is a storage modulus. So if the storage modulus is bigger than the loss modulus, then it's a solid. If the loss modulus is bigger than the storage modulus, it's a liquid. It's a viscoelastic. It's got some solid, some liquid, but when you're below that point, it flows. When you're above that point, it doesn't flow. So this is called the crossover point. So rheologists will just talk about the crossover frequency usually. Here it's a crossover time, it's 1 over that frequency. Why this is liquid at low times and solid at late? Oh, I guess it's well, maybe it's because I guess it's because the thing is gelling with time or something here. So it's a little bit more complicated than a normal, just a static sample. It gels with time, that's what it is. So it becomes a solid after time. Anyway, he determines that gelation time. They can plot, so at that temperature and concentration, he measures the B2 for either from a simulation or from a neutron scattering experiment. And like this is a simulation, this is a neutron scattering. So blue, I mean the top ones are the neutron, the bottom ones are the simulation thing. And he does 2 or 3 simulations. So this is one of the simulations. So the idea is that if you plot the viral that he measures, which is the temperature, versus 1 over time. So you want to go to infinite time in order to find like the infinite gel temperature. In other words, that's the best one that you can get. You've waited forever, right? So this is a linear dependence between temperature and this time, inverse time. So you get to infinity time by going to 0 inverse time, right? So you can't measure infinite time, but you can measure sometimes and draw a line through it, and then get that what he calls B2 star infinity, which is that's a temperature of that's where the gel at that concentration, that's the infinite gel point. So in other words, if the gel point's a moving target with different times, then you can't exactly study it. So you have to find a gel point that isn't a moving target, and you find that by extrapolating to infinite time. So that's what he does. It gets that B2 infinity star. And then that's what he's going to plot as this like a phase diagram someplace. This B2 infinity star versus volume fraction. And he gets, that's his, like, he doesn't call it a phase diagram. He calls it a state diagram because it's not, I mean, a gel, who knows what a gel is, you know, it's not really a phase. So, I mean, it's jello. So if you want to think it's a phase, it could be a phase. He calls it a state to get around that. So it says like what's the difference between a state diagram? I mean, it's because it isn't a phase, but he's making a diagram like a phase diagram. So he calls it a state diagram. That's the point there. Then all right, so he's got the 3 in that. So when he goes through that routine, so it's a little involved what he's doing, but it's kind of interesting too. I mean, So he's using B2, which is a thermal part, right? And B2 is temperature, so it's basically a phase diagram, which is thermal too. Then he's got at high, so he's saying it, he's distinguishing these three regions. So at high concentration, it's like a phase separation driven, or phase separation in the middle, um, glassy, glass, in other words, when you get to high concentration, the little beads can lock up and make a glass, just like the coffee beans, when you pull a vacuum on it, it becomes a brick. The thing they don't make anymore. But have you guys seen that? Or okay, good. I'm glad, because I've never seen it in the store recently. But if you take those and you just like slice it, the volume of the thing doesn't change any, but it's a liquid, like it moves. So it's exactly what this kind of glass thing is. It's also kind of almost exactly what percolation is. It's kind of almost exactly what phase up. So these things, he's making a distinction between things that are the same thing, you know. That's one issue with this paper. Like what's the difference between percolation? It's just another way to look at glass formation. It's just a statistical way to look at glass formation. So the phase separation probably is the same kind of thing. Anyway, so that's what he does. He gets those things, and he distinguishes between the three regimes and relates them to the three mechanisms. Like Cates, who's kind of like god of science from the UK. So there's a story like de Gennes won the Nobel Prize in France, but he did it with the work of a guy named Edwards at Cambridge, right? So just like Florey won the Nobel Prize on the work of a Russian, right? And the Nobel Prize gives out by country, like, you know, so basically India usually gets left off, like Raman won it, but that was a gimme, right? So basically it's going to go between the European countries, Japan, maybe China and the US, right? And it's going to rotate. The US isn't going to win it 3 years in a row. Actually, they're not going to win it 4 years in a row. So we'll have to rotate between countries. So if you live in England and France won it, they're not going to give it to England the next year to the guy who actually the work that the guy won it for, whatever, right? So Edwards should have won it. He was knighted instead. That was kind of a bonus prize, whatever. Anyway, so Cates was Edwards' student. So it's almost like a legacy, like they owe one Nobel Prize to England. And this is kind of like the most famous student of this other guy. So despite that, I don't think Cates' work is really that important, but basically it's going to go to him probably. So it helps to cite Nobel laureates because there are citations, like people cross-cite papers. Your paper will get cited more if you cite Nobel laureates. It helps, you know. So, but basing the whole premise of your life on that kind of pseudo Nobel laureate guy's work is kind of a funny thing to do, you know, because that's what this paper is more or less doing. Anyway, so there is a long story to that, but that's kind of where this is coming from. And then what else is in here? So then he does microscopy to show, oh yeah, that's a glass. Oh yeah, that's phase separation. Oh yeah, that's percolation. So they all look the same to me, but you know, what am I to say? But this does kind of look like spinodal, kind of, right? So in the middle part, I can see, but the first and the last are the same. And then he goes through how, I mean, what Cates also said was that you could use this to control the structured gels and somehow rule the world, you know, with this thing. So he has a section on how to rule the world is the last section. How you could use this to control whatever. I mean, gels are used all over the place, right? Jello, you know, other things like Jello. I guess he says concrete is a gel, which I'm not sure where that came from, but maybe it is a gel. And then biomedical drug delivery, ocular implants, whatever. So there's gels all over the place. I mean, rubbers are kind of a gel, so tires. So anyway, I think it's an interesting little trip to take, like going through this paper. It's a little challenging, but hopefully you can get something out of it. So gel forming network, he says those three things. How would the thermal dependence gelation differ for these three mechanisms? He kind of talks about that, you know. So it takes longer if you're dilute, and dilute is where he's saying he has percolation, and then phase separation is intermediate, and glassy arrest is really fast compared to the other two. So that's a time dependence. The thermal dependence, phase separation is directly thermally dependent. Percolation depends on kinetics of the particles. It's a kinetic mechanism. And glassy arrest is also kinetic. So those two are going to depend on diffusion coefficient. This one depends on free energy. So the temperature dependence is different. for the three. And then under each of these three mechanisms is gelation of thermodynamic transition. So I think you can safely say it isn't, or maybe it is. Depends on how you want to look at it. It's similar to a glass, so any answer would work. But the safest answer would be no, it isn't, and because it's not, there's no phases that you're really forming. I mean, if you have your shoelace and it's like we had a homework like that, right? You have a shoelace, it's untied or it's tied. Is that a phase transition? That's kind of what a gel is too, right? It's like, so I'd say no, but you could say yes if you want to. What role would kinetics play in each of the three mechanisms? So that's the thing. Percolation is the fastest is glassy, the slowest. This is from him, you know, the glassy is fast, percolation slow, phase separation in between. And then what's the difference between state and phase? It's because he doesn't want to say it's a phase. But he's still, but all the arguments he's making are that it's a phase. Demonstrative premised on Kates, for example, the quenches at different rates could be used as a means of controlling gelation behavior. That's the whole premise of what he's talking about. Then whatever I said about minimal gel point, the extrapolation, that could be a long answer or it could be short, depending on how good you could say that. That's question one. Explain how the second rule for non. So if A is 0 in the van der Waals, you just get the B is the excluded volume. So that's sigma cubed. And the coarsest way of looking at it. So that's the second fill coefficient for hard sphere. And then strain, solid, liquid, measurement at different frequencies. So this is for a single, like a polymer, right? Fluid, viscoelastic fluid, so or a surfactant. Where the short time is solid, short time is liquid, long time is liquid, short time is solid. And then in this case, the time is actually like a reaction time almost. So the thing's gelling as you go along. It's like a reaction. So it doesn't exactly follow that. Probably shouldn't have said that. So there is a crossover frequency though, or crossover time. And that's the gel time for him. B2 equation 1, B2 van der Waals, blah, blah, blah. How would Fenton's figure 3a be used to predict phase behavior? Explain three regimes. So he goes on about the three regimes. First he makes the observation of the three regimes. And then the whole back section of this is about the three regimes, like how, like this figure 4 is supposed to demonstrate the structural basis of what happens. And then he's also got data from actual phase separation for the system, then his gel point stuff, and he's got something on the glassy formation thing over here. So he's kind of tried to tie the whole thing together. So then this isn't in the paper. So if these three techniques, like, well, if you do so he's using neutron scattering, computer simulation, and rheology, like three separate things to look at this phenomenon that's going on. So rheology is going to go from a frequency of like 10 to the minus 4 hertz to a hertz, something like 4 orders of time. So forever to like almost instantly. And then so you can think about like a bell and you ring it and the frequency has something to do with the size. That's the easiest thing to think. So you're talking about 4 orders of size in a rheology measurement, right? From like macroscopic. So if you talk about gelation, all right, things can gel on it. Like if you do a computer simulation with just a 12 by 12 box, you can get it to gel instantly. But if it's a 5,000 by 5,000 box, it could take a very long time for it to percolate across the entire box and make a gel. The gel would be its solid, so something structure has to hold it together. It can't be liquid in that connection, so it has to be a direct link. Anyway, so the size scale matters, like with gels. Like what size scale you look at makes a difference. The neutron scattering, you're looking across 4 orders of size. And then in rheology, you're looking at across like 9 orders of size. It's a huge range from angstroms to meters, centimeters at least, at the lowest frequency. So anyway, So it could be that you're looking, in other words, it's going to impact the measurements that are going to impact that. And if you're comparing computer simulation, which is basically just single beads, right? In other words, really the gel for the computer simulation is a really small sample of a macroscopic system. In other words, in the macroscopic system, you have gazillions of beads, uncountable numbers. In a computer simulation, you have to have a finite number. So it's going to be at least billions of times smaller. And the gel point for that billions of times smaller could happen a lot faster than the macroscopic system that you're measuring in rheology. The neutron scattering is kind of in between those two. So anyway, like there's also a size scale dependence to gelation that he's completely ignored in mixing and matching his techniques. So each technique is sensitive to a different size or a different range of sizes. Right. So anyway, that's a problem that you could ask the guy. Like if he gave this talk, that would be the first question to ask. Like, did you consider that the things you're measuring are like apples and oranges? So you can't make a plot of apples versus oranges unless you mix them or something or do something. I don't know. Anyway, so that's kind of like trying to get somewhere with it. I think to me, it's an interesting paper. You might find it really too challenging or something, but hopefully you can learn something by looking at it. It's supposed to be, P&A is supposed to be that you could read it, you know, that's the idea of these journals. So should be that you could get something out of it. We'll see what you can get out of it. There's also supplemental, this got fine microprint. It doesn't really say anything. It kind of tells you how to do the lamps. Hey, there's some pictures and things. It isn't, I looked through it, it isn't really very useful. He's got the 3 regimes. I don't know. You can look through it if you want. But anyway, the actual guys comment on tomorrow at 12:20. So then there's 2 questions here. So that's one. So that should take up like half an hour. And this one should be, I don't know. This one should be easier, I think, because it's pretty directly. So this is so they found out that if you put an AFM and you put some kind of ionic fluid in it, that the stuff crystallized at the tip. Like so you're doing the AFM, there's an atomic fluid, and you aren't getting the structure you want to see. You see like this thing crystallizing. So it's kind of interesting. So this guy, this is an old, I think this was a qualifier question, you know. So this is like 2021. So it's a few years ago. Anyway, so he's going to model that with the Gibbs-Thompson equation for particle size crystallization, like this thing us here. So this is the Gibbs-Thompson, right? We have usually it'd be 2 sigma over the enthalpy of transition, like the crystallization transition. And then the delta T would be down here and the infinite temperature would be up here. For an infinite crystal, TB would be like he says bulk, that'd be like an infinite crystal. And then that would give you the size, which would be, I guess rho, or H would be the size here. So H would come up here, that would be the size. Then the rho takes care of this is surface, that's bulk. Then you get a size out of it. So the size normally Gibbs-Thompson would be like the size equals 2 sigma over delta H times delta T, and there's a T in the top, a T infinity in the top, would give you like a nanoparticle size. So here he's doing a thing where he has a wall, like the AFM tip, and he's got the liquid phase and he's got the solid phase. So he's got the difference between the liquid and the solid, instead of 1 sigma here, which would be like crystal versus melt, he's got another phase, he's got the wall. So he's got to talk about the difference between those, the surface tension of the liquid, surface tension of the solid with the wall gives him basically the sigma that he wants. However you want to justify that in your mind, but that's what he did, right? So that's just the Gibbs-Thompson equation written for that scenario, that the thing touching the, so it makes a little box down there. It's got a height capital H, which is unfortunate because enthalpy is also capital H. I don't know why I couldn't call that L or something, but and then the particle, the crystals are in there, and then he's got the surfaces. And then he does a Monte Carlo simulation does a calculation, it does a Monte Carlo. The experiment's already been done. So he uses a literature experiment and he does this Monte Carlo where he can see the crystallization happen as he changes something, the thickness. But shifted bias step, that's something different. Somewhere he has the thickness and the melting point shifts due to the thickness. So this is kind of a Gibbs-Thompson plot. T star is like delta T over T. This is 1 over H. So 1 over delta T, the quench depth would be go with this size, which is H here. So that's kind of a Gibbs-Thompson plot. It looks like it didn't work exactly perfectly, but so anyway, so that's the deal. So he's going through the Gibbs-Thompson for that scenario. So the question is like, how do you do that? Or how does he do it? So first he gives this thing. So this is so like the question is like, what is omega here? Right. So if you like we had that like if you write out the my blank paper is obscured. Yeah. Oh, I should write down what he has first and put that down. Got omega equals u minus ts minus mu n equals p a h plus 2 sigma aw, and then u equals ts minus p a w h plus 2 sigma aw plus mu n. So you've got like that thing. So this, like if you, so one question is like, what is this then? Right. So you have if you have that thing, and you have like A is UST, right? So A equals U minus ST. So you have U minus ST, so that's this thing is a Helmholtz. And then somehow he figures out that I think by using the Hoffman, using the Gibbs-Thompson equation, he gets like this expression for this. And then also from this, you could say like, well, just from this, you could say U equals A plus ST. So then you just have plus S, U is plus ST, and then just plug in the A, the U for this. Let's see, just plug in the omega for that. So you plug in this thing in there, and it's this thing. And then there's another chemical potential times the number of atoms in the gap. So you can get U from that. So that's the internal energy, right? So it's kind of like there's a question that just says like, where does that normal Gibbs-Thompson, blah, 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 derived Gibbs-Thompson. So we did that in class, like the Gibbs-Thompson you get from for planar crystal, blah, 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 blah. So that Gibbs-Thompson is just the balance of the the second one is like, he gives these two equations, what are they? What kind of, so it's a Helmholtz free energy, constant volume. That's a kind of free energy. And then Gibbs is constant pressure. So then let's see, oh wait, what does it say? He gives, that's just the thing that he gives. So T minus Tm bulk over Tm bulk, and 2 sigma minus sigma, and then H rho delta H is a gap length, I think. So it's the same, like you just have to go through the Gibbs-Thompson thing. So you have like G, delta G is delta H minus T delta S, and delta S, if you're at infinite T infinity, then delta G is 0, so that means that so delta S is delta H over T infinity. You substitute that in, so you have delta H times 1 minus 1 over T infinity, and then you're going to add in the surface energy. So you have like sigma times the area. This thing is times volume. Take volume here, which is, say it's r cubed, and say area is r squared, and then use gamma instead. And then if you set that equal to 0 with Gibbs-Thompson, you have to get rid of that, get rid of the 3, and just have r equals sigma over delta H times 1 minus 1 over T infinity. And if there's two surfaces, there's a 2 here. Like it's 2 sigma r squared. If you have two surfaces like top bottom. So so anyway, and then you can multiply by T infinity, and you have T infinity and minus T, and this is delta T. It's quenched up. Right. So anyway, that kind of works out. The negative, there should have been a negative, so it should be negative and plus here. Because the T, let's see, maybe it's okay the way it was. There. All right, so anyway, that's the Gibbs-Thompson. For his thing, his R is at H, so it just changes the geometry of it. Like it's H, still two gamma, and because it's gamma, so you're forming, normally in the Gibbs-Thompson, you're forming some particle of size R, but here you're forming crystals within this thing, and some of the crystals, you're saying the surface interactions impacting it. So this is the surface effect is only at that point. So it's like gamma solid wall, and then there's gamma liquid wall. And when you form a crystal, the solid wall displaces the liquid wall. So you end up, instead of sigma, you have the delta sigma. However you want to say that. That's just how he did it. And then the rest of it's the same, right? The rest of it is 2 sigma, and the rho is because to deal with this volume area thing. The rho's in there. I'm not sure why the rho's there. But basically, like you can just do the Gibbs-Thompson and get the same thing. You don't need
What's
to.
on the numerator? Sorry, it's 2 times.
2 sigma times
No,
the
at the very
infinite.
start. 2 into gamma minus.
Yeah, so his T infinity is that, so that would be up here. So it's 2 gamma minus gamma. The gammas are like solid wall minus liquid wall.
Oh, okay.
So those are the 2 things. So you have 3 things in the system. You have the wall, the crystal, and the liquid. So you don't have just one sigma. It's the same thing. It's just the same. It's just that the difference, the action's all at the wall, so it's just the sigma wall.
Okay.
You know, so the only sigma part is at the wall, and that's the interaction between the crystal and the wall and the liquid and the wall. Right, so it's kind of the same. I mean, anyway, you can fiddle around with it. Basically, just do the normal Gibbs-Thompson. That's probably good enough, you know.
You were using sigma and gamma, kind of thinking same thing.
Yeah. Yeah, sigmas and gamma are both surface energies. I think gamma isn't gamma is like the liquid surface tension, and sigma is like for solid or something.
Yeah, no, that's right.
Kind of I get them mixed up. I just use whatever, but anyway, so that's that thing. And then there's this business, blah 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 blah. You can integrate to get the you can get the Gibbs-Thompson equation. I should make this bigger. Here. Those are pretty small. So you can get this. All right, so I'm not sure why this is. All right, so this is the Clausius-Clapeyron from class. So the T squared thing. So this will give you delta P over P gives log of P 2 over P1. And T over T squared is ln of 1 over, is derivative of, so derivative of ln of P, derivative of 1 over T. dt over T squared is derivative of 1 over T. So you do plot of ln P versus 1 over T from this and get PL, which are, usually get the enthalpy from that. PL is the enthalpy, but here, what's PL here? Like the enthalpy of vaporization, but anyway, so the Gibbs-Thompson is kind of this equation. It's basically if you take the derivative of this, let's see, you integrate this. So if you integrate dP over P, you get ln of P over P. And then if you integrate dt over T squared, which is d1 over T, you get 1 over T. So then P of R gives you is all the rest of the stuff. So basically just integrating that will give that. And this is the Gibbs-Thompson saying that the pressure, what's P of R here? Anyway, this equation will give you that equation. P of R is pressure. This is for the pressure of a droplet. Right. So that's the Oswald-Freundlich. It's the pressure of a droplet in terms of the size of the droplet. So the size goes, so it's an exponential dependence on the size. Pressure goes through the roof within the droplet as you get small droplets. The Oswald-Freundlich is the thing with the particle size goes with the concentration, which is kind of like the same exponential of the concentration. So just that's from the notes, like that's in the notes. It's the same equation, but with concentration instead of pressure, or concentration instead of enthalpy or something, surface energy. So anyway, this is just kind of like, this doesn't really have to do with the paper. This is just like asking to do some kind of a transform. Then he uses Metropolis method. Melting point in figure 9 where N is a density, T is use a 612 potential, blah, blah, blah. Monte Carlo's involved transition, give an algorithm for Monte Carlo for Metropolis. So that's basically from class, you know, just saying like what is Metropolis Monte Carlo. So it's just like you randomly do stuff, it lowers the free energy, you accept it. If it raises the free energy, you compare it, a Boltzmann factor of that, like exponential of that energy change over KT to a random number. So that'll be a minus energy change over KT using a number smaller than 1. And then compare that with the random number between 0 and 1. And if your number's either bigger or less than that, then you accept it. Like, it doesn't matter if you say bigger or less. You accept it under some condition based on that probability that you get from the Boltzmann factor. That allows you to accept things that would increase the energy so you can overcome like energy humps. You can let the thing like equilibrate. So that's in the notes too, I think, somewhere. It was in another homework too, like what's a Monte Carlo?
I remember doing Monte Carlo. I don't know, did we do Metropolis?
Metropolis is that method. Monte Carlo, Metropolis is a guy's name. It's a Greek guy. It sounds like it's Metropolis, like Superman, yeah, but it isn't. It's actually a guy's name. He's named, I mean, I don't know how he got that name, but, and then Monte Carlo just means flip a coin. So Metropolis method is the thing I describe, and Monte Carlo means flip a coin. So Monte Carlo, Metropolis is coupled together. It's the same thing. So, as far as I know, but how do you determine the simulation had reached equilibrium? So you can never tell if it reaches equilibrium. So you just say like, what, I mean, you can see, all right, that's a good question because all right, so he doesn't reach equilibrium. Like he has, so he reaches, so he shows the pitch, he shows graphics. All right, showing a graphic from one of these things isn't really that useful because, so does he reach equilibrium here? You know, I mean, it crystallizes at the interface and is a gradient in the thing. Is that equilibrium? I don't know. I mean, basically you would plot density versus time and see if it reached a plateau. But the bulk density of this thing So who knows? Like it would be pretty hard to tell you reached equilibrium here. It's a good question to ask about it. He shows another picture here. Let's see. Shows that one. Oh, that's it. So he has like the dot thing in the an array is a crystal, and the other stuff's a liquid. Looks like the liquid's denser than the crystal. So it's a little odd, but so so anyway, he does that business, and then so how do you tell when it's reached equilibrium? That's like the main question, right? So basically you plot density versus time, and when it reaches a plateau, that's it. But for this case, it's a gradient of densities, and he's got crystals in some regions, some in others. So it's pretty much up to grabs where it reached equilibrium. The answer to that is you're happy with the answer. That's your equilibrium, you know. So in figure 9, it shows that crystal structure. So here, this is the issue of that picture. That's figure 9, right? Oops. So yeah, he shows that that's figure 5, 6, 7. I guess there's a 9, 8, 9. All right, so good. So here he's got like he's got showing the transition, I think. So but this is the liquid state and this is the crystal state, but he's got like crystal in the liquid state at the interface, like his AFM tip is here. It's the same material top bottom. He gets a crystal to form at the edge, you know, so there's an obvious answer to why that happens. I'm not sure he mentions that, but so basically the free energy barrier for crystallization is a half for heterogeneous versus homogeneous. So crystallizing in the middle is going to be much harder than like twice as hard as crystallizing at the surface. So that's heterogeneous crystallization, right? And the phase size in heterogeneous is like half the size, or something smaller than half, right? So you get much smaller phases for heterogeneous, and it's much easier to crystallize. That means if you have a choice between heterogeneous and homogeneous, you're going to heterogeneously crystallize on a surface. You would always choose that because the energy is half as much, right? And the size is half as small. So your stable size is much smaller. So it's less than half. There's some ratio, I forget what it is, but so that can definitely explain the observed behavior, I think, as far as I'm concerned, but maybe not for him. But so you see in the simulation, it crystallizes at the surface because that's a heterogeneous crystallization, and the rest of it's homogeneous. Anyway, the whole problem could be just framed up in terms of heterogeneous crystallization, not in terms of Gibbs-Thompson, if you want it, you know. So it's kind of like this whole thing is really looking at heterogeneous crystallization. It's a question of like how deep does that heterogeneous go into the melt? And then anyway, you could frame this differently if you wanted to. You kind of do the whole thing differently. Anyway, so that shouldn't be, this one should be much easier than the first one. I mean, it shouldn't be easy, but it should be easier than the other one. And then, so hopefully that's all right. See how you can do on it. I mean, just try to answer everything. Right? Put an answer down for everything, and then I can sort it out. It won't matter that much. Basically, just try to answer everything. If you put a coherent answer, that's pretty useful. Oh, I see what the problem is. See this last bracket? I bet I needed that last bracket because the thing existed, right? I found it. Let me see if that works. With no period, but with the last bracket. Yeah, no, that didn't work either. Well, I did find that thing though, so I found it pretty easily. Someplace here. Oh, I lost it now. Here it is. Like if you just Google 1.6 colon the second virial coefficient, I'll get you there. I'll try to fix that link. I think if you just Google this thing, that's probably unique text. Really unique. Yeah, it takes you right there if you just Google that text. So that's that equation. So this actually has everything about the virial coefficient. It's probably also in the wiki page. This one just, like when I opened this, it immediately had the equation I wanted. So anyway, Any comments or anything on that stuff? Friday, like, if you can't do it by Friday, I think that I have to turn in grades on Wednesday or something, so.
I think it's 13th, yeah.
So Friday will be good. You know, and if you have questions, you can email me. I should possibly answer. So that's that business. I have, anyway, I have someplace here. I had the PowerPoint open here. Let's show up down there. Trying to put this. Oops, let me open another one. All right, so anyway, there's a lot of stuff. So there's 25 minutes and there's what? 102. So that's about like 15 seconds per slide, I think. Yeah. There we went through a lot of stuff, you know. I don't know. Like it went through a bunch of equations initially, heat capacity equations, like how do you get CB, CP, like why they're that format, and then what the relation between the two are. This is the same from that paper, right? No, that's the Gibbs-Thompson thing. The second slide on this thing is like basically that same thing. I mean, this is the governing equation for nanomaterials, right? So you have to kind of think about it. Yes. Then you can get the relation between CP, CV by doing some math, some kind of differential math. You can get that expression. And Gibbs-Duhem, so the Gibbs-Duhem you use, so you use it in weird places. So it shows up with the it shows up in the surface things. It shows up like in odd places. So when you get desperate, you use this expression, this derivative of the chemical potential, right? Or in the phase diagram stuff, you use this. They use it in a bunch of places, actually. It shows up in a weird place, and they'll say, oh, it's a Gibbs-Duhem equation. It's this business with the derivative of the chemical potential, and that would be like the derivative of the log of the activity, chemical activity, right? To get the free energy, like KT, mu would be KT ln activity. And then if you want to know, like, how does the activity coefficient vary? If you have one to get the other, you use Gibbs-Thompson, Gibbs-Duhem. So anyway, it's basically just this weird, normally you have the number times the chemical potential gives you the free energy, because this is the derivative of free energy with respect to number. So you normally multiply that by dn to get g. Then there's this other term. So if you do a full derivative of that, you end up with these terms, the derivative of the chemical potential. Then you just mix and match equations and you end up with this expression. This term drops out. The mu dn term drops out because anyway, that term drops out, and this term, that's you end up with this expression. So anyway, you can go through that if you want, but I'll skip it for now. See what else we have. So that was kind of like background stuff that you're supposed to carry through from undergrad. There's some other place. Oh wait, there's more to that. There's also this Clausius-Clapeyron, which is also in this paper, the 1/t² thing. I think someplace in one of the questions has this, and this is the same as the Van Hoff equation for chemical reactions. Well, that's an enthalpy of reaction, and then this is the reaction coefficient replaces the pressure. And it's derived, that Van Hoff is derived the same way, but with you talk about ln of the chemical equilibrium constant, K, which is the products over the reactants composition, gives you the free energy. So it falls, anyway. There's a derivative of that in here too. So it's the same equation you end up with. So the same form is to determine the vapor pressure of a liquid and also to get the chemical reaction coefficient and the enthalpy of reaction so you can measure the chemical reaction coefficient because you can get the compositions of the reaction before and after, but you don't know the enthalpy. I mean, you could measure that in a DSC or a calorimeter, or you could measuring the compositions is a lot easier, and then you can get that enthalpy from this. Everything else, you know, the temperature and the gas constant. So anyway, those are just equations you should have run into at some point. So they're here to remind you. And you can see like these equations show up in papers. That's the thing. Like people just say Clausius-Clapeyron, or they'll say Gibbs-Duhem. So you have to kind of roughly know what those are. You should feel a little bit warm feeling when you see them, because it's like all the rest of it will be like some derivation, and one Clausius-Clapeyron, at least you know what that is. Right. So it'll be a lot of stuff. These are like lifesavers. That's the idea. There's touch points where you've kind of should have seen it before. So anyway, then we went through single component, which is like that's again Clausius-Clapeyron, but the way they use it, the way it's used is that you put in, so if you reduce all the pressures, so there's a point that you know, like the critical point is tabulated for everything, every single phase material. So you have the critical pressure, critical temperature, critical density or volume, specific volume. And with those three, then you can define, then you can talk about the reduced pressure, P by PC, T by TC. Then you can write like a universal way to get the vapor pressure of a liquid, right? This shortcut vapor pressure thing, which is like reduced parameters. So you need TC, PC. You could use omega, and then you can get basically calculate this. And it's based on the Clausius-Clapeyron, just substituting in the
What's omega again?
omega is the eccentric factor. So it's invented by a guy at Berkeley a long time ago. I think anyway. It's a number. It's got some loose relationship to the shape of molecules. So it's called the eccentric factor. That's a fudge factor. I mean, I think there's some trend in shape of molecules, but it's not linear or anything. And it's not monotonic. It's basically a random number. So it's in a table. Is it most thermo undergrad textbooks that deal with chemical thermodynamics have it in the back, like you open the back flip of the book and it's in there with other things. Basically with the critical, if you have PC, TC, VC, then you have omega. That's the third thing. The fourth thing is listed. So yeah, the Van Hoff, it's the same derivation as a Clausius-Clapeyron. And you get the same equation, except instead of pressure, it's a reaction. So this thing is the product mole fractions multiplied by each other divided by the reactant mole fractions multiplied by each other. So that you can measure. Then you can get the enthalpy of reaction from that if you know the temperature. All right, so that's useful. That's just showing something. And then if you want to talk about the temperature dependence, the pressure dependence of glass transition, this is from the book. It's interesting though. So if you say, if you just say you're going to break volume up into temperature and pressure dependence, and then these things, this is the thermal expansion coefficient, that's like 1 over the compressibility. So then you can just say that dT dP for any transition should follow this thing. So the glass transition should follow. Oh no, not for any, for a transition where the volume change is 0, which is the glass that's a second order transition. So any second order transition, the pressure should change with the temperature. The transition temperature should be monotonic in pressure, because this is always positive. You have to have a positive thermal expansion, positive compressibility. So this thing has to be positive. You have to have an increase in second order transition temperature with pressure. for whatever that's worth, but this is showing, I don't remember what this is showing. It's a Neely temperature. I don't remember what it's showing, but it's a heat capacity at the transition for second order. We talked about that some. This is isochoric phase diagrams. There's a lot of stuff we went through. Gibbs phase rule. It's like if you have one component system in one phase, then that's in a space, an area, two degrees of freedom. If you have two phases like liquid vapor in a one component system, then you have 1 degree of freedom, so that's a line in like a PV plot. And then if there's three things like liquid vapor, solid, a triple point, then this thing, you have 0 degrees of freedom for one component system. That's a spot, that's a point. That's kind of the idea. And you can do that to any, anyway, I think you've seen that before. Then we went through, like, this is the van der Waals equation. So you take the ideal gas law and you say, I'm gonna have a volume, so the objects can't fly through each other. I have a volume that increases the pressure. So it's going to subtract from the volume in this equation. And if I want to have attractive interaction between the particles, that would lower the pressure. So it's negative, and that's going to be binary. So it's the density squared, 1 over the volume squared, specific volume. Right. So that's the van der Waals, the simplest cubic equation of state. Cubic because it has 3 roots. So you have plot out pressure versus volume, and then you say you're at this pressure, you have 3 volume choices, like that one, and that one, if you're in the 2-phase region. This one's imaginary, kind of. That one's a low volume one, so that's a solid, and that's, or liquid, and that's the high volume, so that's the vapor, the vapor liquid equilibria. And then the area under this hump and the area under that hump are equal to each other. So that's a Maxwell construction. You take the area, you have the tie line, and the area under those and above that are the same areas. And that kind of defines where that point is. But anyway, so if you have the ideal gas law, its pressure goes with 1 over volume, so it's always like that. If you add in this excluded, if you add in the attractive potential, so you can make a condensed phase, then you get these humps in the pressure volume curve. So that would be the pressure volume curve for the van der Waals equation. And then basically it's going to look like this, and then you just draw lines between those, and that gives you the phase boundary. So if you're within this region, you separate into liquid and vapor, and the tie line decides the amounts of that. That's kind of the idea. So then we did Landau's thing for a little while. So it's basically, he introduced the idea of an order parameter, which was originally the magnetization. So that kind of the arrows of the magnetic domains, which direction they're pointing. And then it's generalized to like phase separation. So it would be like concentration, or like if you had the average density and then the density of the phase. So that would go to 0 when you get to a single phase. That would have a value when you're in 2 phases. Or the magnetization would have a value when it's magnetized, and 0 when it's demagnetized. So this order parameter has a value or it's 0. It's positive value or it's 0. Right? So it goes to 0 when you're at the transition point, the critical temperature. So his Landau's proposition is that it's analytic. So some function between order parameter and temperature that governs the free energy. And the free energy will be symmetric in this order parameter. So it has to be even powers, like squared, fourth, whatever. And then you end up with this kind of expression that we saw before, like the T minus, so this thing that was in the Gibbs Thompson equation, like T minus TC over T, like the delta T over the different distance, or the quench depth, or the distance from the critical point becomes like a governing temperature. The critical point becomes like a 0 point of temperature. So your temperature scale starts at the critical point, right? And then, anyway, so those ideas all came out of this order parameter thing, right? The idea that you have this temperature scale based on a critical temperature. The word critical temperature came from this Landau theory. The whole critical point, critical temperature, it's all from this, basically. Anyway, so we went through that. It's a lot of stuff. Then mixing, ideal mixing, we did like 3 different ways, like pressure, volume, and then statistical, and then also 4 ways. And then we did it from statistical mechanics kind of approach, the Boltzmann thing. We get the same equation, x ln x plus x ln x, so entropy. And if you want to have non-ideal, you swap out this x with the activity, or with, which would be, activity would be x times gamma, the activity coefficient. And then you can get various forms of this thing, like the Gibbs of mixing would be the activity, and then the excess would be like that mixing minus the ideal. So that's the distance you are from the ideal situation. So this kind of thing leads to this idea of departure functions, like this excess Gibbs. You could make up a formula for that, and then you could do calculations on an ideal system and then say I'm going to real. So you could start with a real system, go to ideal, do all your calculations on ideal system, and then use that departure function to go back to real. So that's like how a lot of the software, thermodynamic software works, because it's easier to do calculations in ideal systems. Then you just need to know how to change from ideal to real. So if you have this departure function, this excess Gibbs, excess entropy, entropy, then you can go from the ideal back to the real, or from the real to the ideal, and then do all your messy calculations with ideal and come back to reality. Like, so you can go up into an ideal world and then come back. So it's useful to do that. It makes things a lot easier. I mean, it makes things possible because a lot of times you don't have the parameters to do the calculations, whatever you're trying to determine in the real space. So then the real systems, you end up with this Hildebrandt concept that you're just going to add in a term that's like the volume fraction of the two, the mixing, and then the average energy of interaction of the two. And then just add that term in, and you have a real system. So this is symmetric. You can swap out A and B, you get the same equation. So that means the thing is always going to be symmetric, but most phase diagrams aren't symmetric like that. So you can do more complicated things like add in asymmetry. So instead of the 1 omega, you have 2 terms that depend also on composition. That would skew the phase diagram. And you can do that as much as you want. You can do a Taylor series of the difference in A and B. So then you can do anything else you want to do. Like there's hundreds of different expressions for free energy and mixing. And then this is an example of, so that's a Gibbs duum with constant pressure and temperature. So I had a phase. So anyway, so if you set, then you plug in for D, for chemical potential will be ln of RT times ln activity, but since it's equal to 0, the RT goes away, is constant. And then you can just follow through that you have an expression because the x80 ln xa, so ln d ln x b is dx over x, so the x's cancel. So this is just dx db xb, and the sum of those has to be 0. So that means that term drops out. And then if you just say that this is true and that's true, then you have to say that this is true too. And that means that if you know activity coefficient of 1, you can get to the other. So that's using the Gibbs duum. One case of using the Gibbs duum. It says that you can use it to get things you couldn't get. Like how does the activity, binary mixed system, how's the chemical activity relate between one and the other one? So they're related by this integral expression. So anyway, then we did phase diagram stuff. It's like eutectic, and then how to construct that from free energy expressions, calculation of phase diagrams, and then kind of all different kinds of phase diagram calculations. And then the big picture of like you have, if you'd studied chemical engineering, so you have liquid vapor equilibria, and then in materials, you have kind of solid liquid equilibria, and they have mimicking phase diagrams. So in one field, you would never hear of a congruent melting. In the other, you would never hear of an azeotrope, right? So but they're kind of the same things, you know. I mean, they're basically the same thing, except it's liquid vapor and this is solid liquid. So, and you'll never see heteroazeotrope in a chemical engineering, but you always see eutectic in metals, and you'll never, it's kind of like the ones that are important are different. That's kind of the idea. But then the free energy expression gives you the phase diagram by tie lines, right? So you find the slope of dg, dx is chemical potential. The two phases have the same chemical potential. So a slope, the line that cuts the two, is that those two are at equilibrium with each other. And then as you go through different temperatures, so T2 would be the critical temperature where it's flat, and then you get two humps as you get deeper quench. And then you get, this is a single phase. So you just have smiley face means it's happy wherever it goes, and frown face means that it's going to go to two separate things. It'll separate out in the free energy versus X spot. And the two phases is going to be like the two minima in that. And you also get the inflection points, the spinodal line, and this thing, which would be inside, be another one inside. So like here's spinodal, this is phase separation. This is LCS, phase separation on heating, and then so it's upside down thing. So anyway, and then you can have interplay between crystallization and phase separation. So we kind of mentioned that, not much. And then this business, we talked about metastability, and then like how superheating, supercooling. I skimmed through it, I think. I'm not sure, was there a paper, if there was a paper on this stuff, but I think it was spinodal, like mostly, but he goes through a lot of the supercooling, the Kautzman paradox. Like if you plot entropy versus temperature and you look at the solid phase and the liquid phase, if you extrapolate the liquid into supercooled liquid, there's some point where the entropy, kind of the randomness of the liquid, which isn't possible. So you find a point that's the ultimate glass transition temperature. Like you can't have a lower one. It's not possible. Right? So that's called the Kautzman paradox. Is an equivalent paradox for melting point that he went through with pressure and stuff. Pressure with the moduli, right? So anyway, oh yeah, I didn't have that in here. We went through that, the 4-parameter moduli thing too. Polymorphs we talked about. So yeah, this thing's about surface things. Right? So anyway, we went through a bunch of things on surfaces. I think surfaces are pretty important. So we went through all that stuff. There's a ton of stuff we did, Hopefully you retain like a little bit of it. But and then he's got a chapter on this enthalpy, which about just basically trend lines in the periodic table for different enthalpies of formation, heat of formation. And then we went a lot into heat capacity, like 3 weeks of heat capacity, which you may look back and dread, but anyway, I think it's important. It's one of the main things in here. Like, how do you measure it? And then basically Dulong-Petit rules and phonons and vibrations, Brillouin scattering, right, to get the density of states, and then the Brillouin zone business, wave vector frequency thing, how you relate modulus to heat capacity, all that business. So how spectroscopy relates to the heat capacity. It's a lot of heat capacity. Hopefully it wasn't too much. I mean, I think it's important because the heat capacity stuff is the basis of other papers. Like talking about phonons, if you know heat capacity, you know phonons, for one thing. So, I mean, you'll see it, and then to get mechanical properties, phonons are important, right? Anyway, and then correlation function, we mentioned a little bit, and we did that modeling thing like last week or two ago. And then that's about it. So anyway, that's like 25 minutes. Trip down memory lane, but I'm not sure it's worth doing that, but I guess it gives you a feel for like, at least we covered some stuff, covered some territory, so hopefully you got, I mean, I don't really expect that you'll get everything out of it, but just kind of if you hear it again, the idea is like, if you hear it again, it won't be totally unfamiliar to you, like you can say, at least I hated that, I mean, so, anyway, hopefully it'll be helpful. That's about it. If you have problems with that homework, just email me. I don't know.
Thank you.
Thanks, yeah. Yeah, thanks for showing up, you guys. The regular crew.